Hi everyone, welcome back to another video of Engineers Academy. So guys, over here in this video we are going to talk about the second law of thermodynamics. In our previous case we have seen the first law of thermodynamics, which states that this heat energy and work are mutually convertible. We can convert the heat energy to the equivalent amount of work. So guys, over here in this video we are going to talk about the second law of thermodynamics, which contains the limitations of first law of thermodynamics, which contains the statements. These two statements are there, that is nothing but your Kelvin-Planck statement, which is nothing but the law of degradation of energy, and your Clausius statements, which states that the actual heat can flow from cold body to hot body while consuming some other work or while consuming some other source of energy. So guys, over here in this video we are going to learn the limitations of the first law, the Kelvin-Planck statements and the Clausius statements. So guys, if you're new to my educational channel Engineers Academy, just please do subscribe to my educational channel Engineers Academy, and guys please hit the bell icon so whenever I upload a video you will get instant notification. So guys, without wasting any time, let's begin with today's topic, that is of the second law of thermodynamics. So guys, now let's talk about the limitations of the first law of thermodynamics. Now this particular first law of thermodynamics states that the heat and work are mutually convertible. We can convert the 100% of heat to the 100% of the mechanical work. But guys, that is not possible over here in actual practice. In actual practice, there will be always some kind of the loss of energy. If we suppose I'm having an isolated system, let's say our previous example, and the piston is there which is kept in that particular system, and that particular isolated system is having a gas enclosed in a particular chamber, and a piston is over there kept on that particular chamber. Suppose I have like applied heat to that particular isolated chamber. Let's say if I have applied 100 joules of heat over here, the mechanical work done will occur due to the internal energy of the gas. But over here this piston will move upwards, the displacement will be there in meters, and the energy applied, that is nothing but the force applied by the internal energy of the gases, can be termed in Newton. So guys, over here the work done will be in Newton meter. So guys, 1 Newton per meter can be termed as 1 joule. So guys, over here if we apply 100 joules of heat energy to that particular chamber, the net work done will occur, but work done will be less than that of the heat supplied. There will be always a loss of heat. Let's say over here the work done will be of 50 joules, or we can call it as a 60 joules maximum. So guys, over here in this particular thermodynamic process, in the process of conversion, there will be always a loss of heat energy. So guys, the statements, that is the heat and work, are mutually convertible, but it is not 100% efficient. So this is the first limitation of first law of thermodynamics. Also guys, this first law of thermodynamics shows that this particular energy flows from flow of the energy, that is the flow of the heat from two different systems, two different bodies. But over here in first law of thermodynamics, it does not define the path of flow. So let's say the heat flows from cold body to hot body, or hot body to cold body. It does not define the path of flow of the heat between these two particular systems. So also guys, this particular first law of thermodynamics does not states the conditions, like the chamber is isolated or the open chamber, or else the system is closed system or open system. It does not define the state of the two systems. So these are nothing but the limitations of first law of thermodynamics. So guys, over here another statement which is given from Mr. Kelvin-Planck. So he states that whenever like a heat is converted into the mechanical work, there will be always a loss of heat, there will be always a degradation of heat which occurs. So guys, this particular Kelvin-Planck statement says that it is impossible to construct a heat engine which converts all of the heat into mechanical work. There will be always a loss of heat, there will be always a degradation of heat. So guys, this particular statement can be called as the law of degradation of energy. So guys, this particular Kelvin-Planck statement can be called as this law of degradation of the energy. We cannot convert the 100% of your heat supplied to the body into the mechanical work. There will be always a loss of heat supplied. So guys, let's say I'm having my heat pump, and I have connected my heat pump to a particular reservoir which is having a higher temperature, and now I just want to convert that particular heat energy into the work done. So now let's say like over here in this case, my reservoir is at having the temperature T1 and the total heat supplied through a heat pump from that reservoir is Q1. So over here the net work done will be always less than that of the heat supplied. Suppose over here the loss of heat supplied is Q2 over here, and I have collected that particular loss of heat in a particular different reservoir over here. So let's say that particular reservoir, let's say it is a sink basically, and I have collected the loss of heat into that sink. Suppose the loss of heat is Q2. So guys, over here the total net work done will be Q1 minus Q2. Q1 is the initial heat supply and Q2 is the rejected heat from that particular process. So over here the net work done will be Q1 minus Q2. So guys, over here in this particular system, in this particular cycle, the total efficiency of the system will be of total amount of the energy supplied to the total work done. So over here the energy supplied is the Q1, that is the initial heat supplied, that is Q1 divided by the work done. And guys, over here work done is equals to Q1 minus Q2. So over here the formula becomes this Q1 divided by Q1 minus Q2. So let's say in case of temperature, that will become this T1 divided by T1 minus T2. So guys, this is the formula for calculating the total efficiency, overall efficiency of that particular heat engine or heat pump basically. So guys, that is nothing but your Kelvin-Planck statements. So moving ahead, next is the third topic, that is nothing but your Clausius statement. So now this Kelvin-Planck and Clausius, these are the two scientists, and they have made this second law of thermodynamics, which is very relatable to each other. This Clausius statements says that this particular Clausius statement, he says that heat can actually flow from cold body to hot body. But the nature of the heat flows from hot body to cold body. But over here this Clausius says that heat can flow from cold body to hot body by the application of some external energy, by the application of some external work done over here. So guys, in order to understand this Clausius statements, let's take one example over here. Suppose I'm having a cold body and I want to reduce the temperature. I want to just make the heat flow from this cold body to another hot body. So guys, I'm having these two bodies. One is at the cold body having temperature T2 and other is the hot body having the temperature T1. So I place a pump which force heat from the cold body to hot body. Now this pump, to drive that pump, I required some sort of the external energy. Let's say W is the external energy or the work done in case of this pump. Now this particular pump will flow the heat energy from this particular cold body to hot body. It will gain the heat, that is the Q2 over here from this cold body, and it will convert the Q1, that is the heat, to from in hot body. So Q1 is the heat which is at the higher temperature, and Q2 is the heat which is at the low temperature. So guys, this particular pump will flow that particular heat from the cold body to hot body. So this particular Q1, that is the heat which is at the hot body, will be the addition of the external energy by the pump and the initial heat supplied, that is of the Q2. So guys, over here the Q1 will be of the Q2 plus the external energy, external source which is required to drive that particular pump. So guys, over here this is how a particular a heat will flow from cold body to hot body. Now let's say in this case of refrigeration, in this case of the thermal process over here, so this is nothing but your thermal process over here. So guys, we can say that the total efficiency of this thermal process, we can term this particular as a COP, that is nothing but the coefficient of performance, be termed as the total heat supplied to the system divided by the actual amount of the external energy required to produce that particular effect to drive that particular system. So this particular COP is the ratio of your total heat supplied to the system and to the actual amount of the work done or actual amount of the external heat which is required to drive that particular system and to get the effect basically. So over here the COP will be equal to your total heat supplied, that is of the Q2, and your effect will be refrigeration effect, or we can call it as a effect by the heat pump, that is equals to WP over here. So WP is the work done due to that particular pump. So guys, over here the equation becomes your Q2 divided by this WP. So over here WP is nothing but the Q1 minus Q2. So the formula becomes Q2 divided by Q1 minus Q2. So this particular Q2 is having the temperature T2 and Q1 is having, that is the having the temperature T1. So the net formula becomes T2 divided by T1 minus T2. So this particular formula gives us the COP of this particular thermodynamic system. So guys, over here in this video we have seen this three types. So we have seen the second law of thermodynamics, so which consists of the limitations of the first law of thermodynamics. We have seen the Kelvin-Planck statements, the law of degradation of the energy, and also guys we have seen this Clausius statement. So guys, I hope you understood this second law of thermodynamics. So in case of any doubts, in case of queries, you can comment below. Also guys, please don't forget to subscribe to my educational channel Engineers Academy, and guys just hit like, so your like will really motivate me to make more of such educational videos. So guys, thank you for watching my educational video guys. Stay tuned and subscribe to my educational channel.